Well, thanks very much for that kind introduction to begin with. And just your comment on kinesiology. Most of the kinesiology departments in the US are formerly physical education departments. And there was a shift that was initiated late 80s, probably early 90s. People said, if we want to really make physical education a more legitimate area of study, we probably need to change our name. And so kinesiology was the name that sort of caught on because it was scientific sounding. Anything that's got ology at the end, sounds like it's a real scientific field of study. So that's how we all became kinesiology departments, but we're basically physical education departments. Having said that, obviously, the modern kinesiology department does has a lot more breadth than the traditional physical education department. In any case, I'm just going to move my. There we are. So again, thanks for inviting me to give this talk. I mean, the talk is basically based on the paper that Jason was just referring to, and I've titled this talk "Capitalizing on Individual Differences to Facilitate Motor Skill Learning." This is the actual paper. It's titled "Individual Differences in Motor Skill Learning, Past, Present, and Future," and it's going to appear in a special issue of the Journal of Human Movement Science titled "Individual Differences in Motor Skill Learning." So this is an opportunity for me to acknowledge my co-authors, Keith Lowe's, Tiago Lopez, who's a student of Keith and Mark, and of course Mark Williams. And full disclaimer, we wrote this paper, and Mark and I put together the special issue on individual differences because we didn't really know very much about individual differences. But we all thought it was a really important topic. And we all thought it was a topic that needed to be discussed more widely in the field. And so we're hoping that this paper will, serve that purpose. So actually, I'm excited that you've given me an invitation to talk about it here to you. Before I dive into the paper, I thought I probably should just give you a really brief recap of some of the themes that have dominated my research agenda, because as I just pointed out, individual differences is a fairly new area of study for me. So I've done research in the past on the contextual interference effect, on augmented feedback and how it impacts skill acquisition, on critical periods or sensitive periods in skill acquisition, on the control of upper extremity prostheses. And probably the work that I've been focused on most heavily for the last, I'd say 25 years, is research that's actually on infants, and it focuses on how self-produced locomotion, the acquisition of self-produced locomotion, influences psychological development during infancy. And that's actually led also to another body of research that I currently do that's focused on newborn motor development. So as you can see, I'm fairly eclectic here in terms of the sorts of things that I've been interested in, but everything is connected to this general theme of understanding changes in behavior, and particularly motor behavior. So back to the paper, our goal again was to draw attention to the research that has been done on individual differences and motor learning, and to encourage more people to do research in this area. We think that individual differences should be a central topic in motor learning research, and we think that a better understanding of individual differences could not only enhance our understanding of learning and transfer, but also potentially revolutionize the design of practice and usher in an era of personalized skill acquisition, perhaps akin to the personalized medicine approach that we now see in the health sector. So what we did in this paper was basically, first of all, give a brief historical overview of research that had been done on individual differences in motor learning. Then we conducted this systematic review of research that had been conducted since the millennial. And then we talked about some of the methodological challenges that are associated with doing research on individual differences, and we provided some suggestions for future research. So I'm going to, my talk is essentially organized around these three sections of the paper. So starting with the historical overview, there are four critical issues or questions that we looked at. So the first question is, are individual differences better explained by nature or nurture? And this is a question that dominated early psychology. It was prominent in the late 1800s when people were particularly interested in studying intelligence and understanding intelligence. And it dominated research in the early 1900s. The second question was, is general intelligence equivalent to learning ability? Again, this question was quite prevalent in the late 1800s when people were beginning to study individual differences, and it continued to attract attention well into the middle of the 1900s. The third question is, do measures of ability predict learning better than initial performance? And this is a question that was really stimulated by the First and the Second World Wars, and the practical need to identify people who could be trained to perform military tasks. So, the research was really prevalent from the 1930s until probably the 1990s. And then the final question is this one: do aptitudes interact with learning variables? And as you'll see in a moment, this is a question that was really pushed by Lee Cronbach, who was very interested in this idea of the interactions between individual difference characteristics and learning variables. And he published a very influential paper that was based on a keynote address he gave to the American Psychological Association in the 1950s. So what I'm going to do then is look at each of those four questions quickly to give you a little bit more substance in terms of what was really going on relative to those questions. So the first one then is more or less, are individual differences attributable to inherited characteristics or prior learning? And of course, this nature-nurture issue was very prominent in psychology in the late 1800s and early 1900s. And there were some obviously really notable people who were interested in this question. Francis Galton, who pioneered the use of statistics to capture individual differences, was a major player. Galton, of course, did a lot of work on genius and exceptional performance. He inspired people like James Cattell. Cattell is considered the father of modern psychology in the US. He was also very interested in intelligence, and he actually developed a lot of the methodology that we still use in experimental psychology and in differential psychology. And then, of course, there's Edward Thorndike, who was one of Cattell's students. And Thorndike did quite a lot of work on individual differences. And in fact, Thorndike was the one who said that we could determine whether nature or nurture was making more of a contribution to individual differences by looking to see whether people diverged with practice. Did they become less alike as they continued to practice, or did they converge? Did they become more alike? And the premise here was that, if people diverge with practice, then the individual differences must be explained by some sort of inherited characteristic, because they're all now basically becoming more different as they undergo the same treatment, which is practice. Alternatively, if they become more alike with practice, clearly the learning is probably sculpting what's going on here. And so Thorndike actually published a very early experiment using a simple mathematics task, and he found that people tended to diverge as they practiced this mathematics task, and of course concluded that individual differences were attributable to genetically inherited factors rather than learning. Interestingly, though, if you look at the research that happened after Thorndike's original publication, you see that researchers are finding pretty much just the opposite was happening, that most of the research tended to suggest that people converge with practice, suggesting that learning was the more important variable. So the next question was this question about general intelligence and learning. Are they essentially equivalent? And in the early conceptions, scientists strongly related intelligence to learning ability, thanks to work of people like Alfred Binet and Charles Spearman. Binet, of course, came to prominence in the late 1800s after the French inaugurated popular education, and they quickly found that not every student learned with the traditional instructional techniques. And so Binet thought that if he could design a test to identify who these struggling students were, he could then give them some sort of specialized instruction to bring everybody up to the same level. And of course, ultimately, working with his colleague Theodore Diamond, developed the first intelligence test. Charles Spearman was inspired by the success of Binet's intelligence testing movement, and then he developed and popularized the two-factor theory of intelligence, which is actually still prevalent today. And that theory essentially says that the performance on any test of mental function can be attributed to a general ability factor that he termed G, which is more or less a stand-in for general intelligence, and then more specific factors that relate to the specific task itself. So the third question relates to this idea of predicting learning from abilities. And the question is, do measures of ability predict learning better than initial performance on a task? Work in this area began in the 1930s, but was dominated by Edwin Fleishman in the 50s, 60s, and 70s, and then Philip Ackerman in the 80s and 90s. And as I mentioned earlier, it was really the First and the Second World Wars that accelerated a lot of research in this area because of the need to figure out how to train people quickly to perform military tasks. And Fleishman himself was actually in the Navy, and much of the work he did was actually for the United States Air Force, as well as then private companies after he moved out of an academic position. So to understand this question on predicting performance based on initial performance or abilities, I need to say something about this superdiagonal matrix. So the earliest scientists who were focusing on individual differences relied heavily on analyses of the between participant variability in response to task practice. And this superdiagonal matrix, which is also known as the simplex pattern of between trial correlations, traditionally provided the primary index of these differences. So I just constructed this, I made up these data, but just to illustrate the point. Basically, I've got a trial here, which would be trial 1 to 100 to 1,000 to 10,000 to 100,000. And here I've just made up the correlations between each of these different trials at different stages during practice. And essentially what you see is there's a pattern of declining correlations. So as you get further away from the initial trial explains less and less of the variance later in practice. But as you can see, even late in practice, you can still predict a certain amount of the variance in final or later performance from initial performance. So again, the main question is here relative to abilities, can we do better than this by assessing abilities prior to practice, or are we going to get as much as we actually are likely to get by just looking at initial performance and using that as a predictor of final performance? So before I actually get into Fleishman's work, because I want to show you a couple of examples, I wanted to highlight his conception of the relation between ability and skill. And this is this conception that was held by his contemporaries, and it's really the conception that we have today. And the basic premise is this, that if you look at a skill like a tennis serve, that skill can be broken down into sub-skills, and these sub-skills are determined by specific abilities. So these are just some of the abilities that Fleishman identified: multi-limb coordination, control precision, rate of arm movement, and so on. Really should flip the arrows on this, because basically the idea here is that these abilities serve as the substrates for the sub-skills and then the skills that we acquire. So what did Fleishman do? He used factor analysis to identify abilities, and using these abilities, he argued that the different combinations of them explain variance of performance at different stages of practice. So the basic strategy here is to give performers a whole battery of tests that are designed to illuminate some of these abilities. And then you look at the intercorrelations between the performance on those tests, as well as the performance on the criterion task at different stages of practice. And based on those intercorrelations, you can identify what abilities are predicting performance on the criterion task at different stages of practice. So abilities are basically then latent variables. You can't directly observe them. We're inferring them based on this factor analysis technique. So using the technique, this is essentially what Fleishman claimed, that if you looked early in practice, you found that early practice was explained primarily by broad cognitive abilities. In the middle of practice, the variance was explained by perceptual motor abilities. And then late in practice, what he observed was this new task-specific ability emerging. And this was really interesting because it suggested that the best predictor of performance late in practice was performance on the task itself. And of course, this was a particularly vexing finding because it suggested that as practice continued, tasks became increasingly specific, and that measures taken at the beginning of practice were less likely to explain final performance than were measures taken of criterion task performance throughout practice, particularly at the end of practice. So let me just show you a couple of examples of Fleishman's findings. This is a classic study by Fleishman and Hempel from 1956. He used this discrimination reaction time task, which is basically a choice reaction time task. So you've got stimulus lights up here. You've got these toggle switches here. And he looked at the contribution of different abilities at different stages of practice. So this is on the y-axis, the percentage of variance that's explained by these abilities over practice. And you can see quite clearly that the combinations of abilities change that explain the highest variance in performance. So spatial relations tend to dominate early in practice, but then they tend to drop out later in practice. Conversely, if you look at some of the perceptual motor abilities, reaction time and rate of movement, they don't explain very much variance at all early in practice, but they explain a lot more late in practice. Here's another example of that from an experiment by Fleishman and Rich using this two-handed coordination task. This is a tracking task where you use two hands to try to track a target on a turntable. It's equivalent to, I don't know if you're familiar with the Etch-a-Sketches that used to be popular years and years ago, where you use these two knobs to draw things on a screen. So here is two graphs showing average time on target in the task as a function of practice blocks. And in this first graph, you see performers who score high on a spatial measure or low on a spatial measure. And you see that the high spatial measure people dominate the low spatial measure people early in practice. But by the end of practice, there's no difference between these two groups. And again, conversely, if you look at a group that's considered high on kinesthetic sensitivity and a group that's low on kinesthetic sensitivity, there are no differences between them early in practice, but differences are clearly emerging at the end of practice. So Fleishman did a number of studies. He published dozens of studies like this, showing the same sorts of findings, that as practice continued, different combinations of abilities would explain performance on the task. But this task-specific ability still emerged as you got very late into practice. I'm really surprised, I've got to say, that Fleischman's work is not better known, and that we don't teach it more extensively in motor learning classes. I think the reason for that is that he was subject to a lot of criticism for his factor analysis methodology. I mean, basically what he was doing was looking at these intercorrelations between performance on these test batteries and performance on the criterion task, and then using that to predict performance on the criterion task. And people said, yeah, that's statistically, that's not really appropriate. You shouldn't, for one, you shouldn't be using factor analysis to look at dependencies between independent and dependent variables. And two, you're using criterion task performance to identify your abilities, and then you're using those abilities to predict criterion task performance. And again, statistically, that's not really appropriate. So this then paved the way actually for Philip Ackermann to come onto the scene. And what Ackermann did was build a program of research that was basically designed to address the criticisms that were leveled at Fleishman. And he started by reanalyzing a number of Fleischman's original experiments. But what he did was he separated out the performances on these test batteries and criterion test performance so that there wasn't this intermixing of the two. And when he did that, he started to find some different patterns of relations between abilities and criterion task performance. Now, they weren't strikingly different from what Fleishman had found, but nonetheless, they were different. And one of the primary differences was that Ackermann found that when you separated out the test batteries from the criterion task, late in practice, you really didn't see this task-specific component emerging, which was really good news for people who are interested in predicting performance based on these measures taken prior to practice, because it suggested that you could, in fact, explain a significant portion of variance late in practice by focusing on what people could do before they started practicing the task. So here is a depiction of Ackermann's conception of the relation between skill and ability. And I'll just, it's complicated, so let me just walk you through this. So if we look at initial performance on a task, we've got this novel task. Ackermann said there are 4 primary contributors. So the first is specific skills that might transfer to the novel task. So these are acquired skills. Then there are these more specific content abilities that people have. These would be stable abilities. Then there's specialized knowledge that people might have acquired. And then there are these general abilities like intelligence. So these 4 things are determining how people perform initially on a novel task. Then what happens next is a function of the task itself. So if the task is not particularly complex and it has pretty consistent information processing components, then when you get to later final performance, it can be run using automatic processing. And here it's predicted by a number of overlapping skills and processes. However, if you've got a task with that's more complex and has inconsistent information processing components, then you have to use controlled processing, and the predictors will be general ability measures as well as more specific content ability measures. So Ackermann's basically then throwing in this additional variable of task complexity and complexity of information processing to develop a more nuanced set of predictions about what's going to happen with practice. So this is another schematic that pretty much just summarizes Ackermann's ideas. And you can see by the terminology that he relied very heavily on Fitz and Posner's ideas about stages of learning, as well as Schifrin and Snyder's ideas about automatic and controlled processing. So early in skill acquisition during the cognitive phase, performance is pretty much determined by these general abilities, verbal, figural, numerical abilities. As you get deeper into practice, into the associative phase of learning, it's perceptual speed measures that explain the variance in performance. And then as you get into the autonomous phase, it's these psychomotor abilities that explain performance. And this is another way of depicting that in this graph here. So you see the correlations between these different measures at different phases of practice. So these general ability, and this would be for a moderately complex task. So these general ability measures are going to explain less and less the variance in performance as practice continues. Perceptual speed measures are going to increase in the amount of variance they explain and then decrease. And then as we get later into practice, performance is going to be increasingly explained by these psychomotor abilities. So this is just the same graph that I was just looking at, but here is a more nuanced version of it that looks at what happens when you've got tasks that vary in complexity. So one would refer to a task that's more complex and has inconsistent information processing requirements, and four would correspond to a task that is less complex and has more consistent information processing. So if it's a complex task, then these general abilities continue to explain variance in performance all the way through practice. Conversely, these perceptual speed measures will load higher and will load higher on performance and explain more variance earlier in practice than they will if the task is more complex. And in a similar way, these psychomotor abilities will load earlier and explain more of the variance for the less complex tasks than for the more complex tasks. So that was basically Ackermann's program of research. I've got to say that he found considerable support for his ideas, but the support wasn't overwhelming. It's fairly nuanced support, but I think in sort of a broad scope, in the broad scope of things, his research tended to generally support these ideas. Okay, so the fourth and final question in these critical issues that have dominated research is this question about aptitudes interacting with learning variables. And this is where we get into Cronbach's ideas. So Cronbach defined an aptitude as any characteristic that affects a person's response to to treatment. So it's obviously pretty broad now. So abilities would be a subset of aptitudes. And Cronbach argued for combining the approaches that were used by experimental and differential psychologists. He said the greatest social benefit will come from applied psychology if we can find for each individual the treatment to which he can most easily adapt. Now, prior to this call in 1957, the experimentalists were focused on group performance, and they wanted to treat everybody alike. And so they searched for the best possible treatments that would work for groups of people. In other words, the experimentalists, experimental psychologists, were basically interested in examining the central tendency and figuring out how to improve that central tendency. In contrast, the differential psychologists were interested in explaining the variance, and they focused on individual performance, and they wanted to actually treat everybody differently as a way to promote general performance. So most of the work on aptitude treatment interactions has actually been done in educational psychology. There's not a whole lot of work within the modal learning domain that would fit under this label of aptitude treatment interactions. Though there are some notable examples that we could point to. So Craig Hall's work on imagery ability is one body of work that would fit here. So, Craig has shown that imagery ability predicts who will benefit from mental practice. There's some work showing that cognitive style predicts the benefits of random practice. People who tend to be more reflective benefit less from random practice. People who are more impulsive tend to benefit more. And there's some work also that's been done showing that preferences for adopting a particular external focus, particular attentional focus, predict the effects of internal and external focus of attention. And then I think we could say that Mark Guadagnoli and Tim Lee's Challenge Point program would also fit within this aptitude treatment interaction framework, because their framework argues that the most effective learning strategies are a function of the interaction between task characteristics, skill level, and the information processing characteristics of the learner. So that seems to fit really nicely within this rubric of aptitude treatment interactions. So in the paper, we ask whether we could potentially push an individual difference agenda in modal learning by building on some of the research that's been done on self-controlled learning. We know that giving learners control over aspects of their practice is one way to individualize practice, and it seems in general to enhance learning. So there are some interesting questions that we could potentially ask here to build out an agenda. One is, do individual differences exist in preferences for different types of instruction, like implicit or explicit instruction? Two is, do differences exist in the need to be challenged or not during practice? Are such differences mediated or moderated by psychological variables like self-confidence, conscientiousness, or grit? And to what extent do preferences for different types of instruction or practice predict learning? And we started to actually dabble in this area. I've been collaborating with a colleague at Western Sydney University, and along with a couple of students, we did this experiment recently that looked at how people responded to different types of practice structure. So we're interested in deliberate practice versus this practice that we kind of labeled a play-based practice. And the primary difference between these two different practice conditions was, in the deliberate practice condition, we told participants that they really needed to focus on achieving the goal of the task. And in the play practice condition, we said, look, here's the goal of the task, but what we really want you to do is approach learning the task in a very playful way and not be too concerned with achieving the goal of the task. And one of the things we did was actually measure the extent to which they followed those instructions. And well, what was interesting was we found that there was a lot of individual difference in whether people actually followed the instructions they were given. And that actually made a difference in terms of how they performed. So the task we used with this was this stick test of coordination. The goal is to try to flip this stick 180 degrees and catch it. And so the dependent measure here is the number of successful flips they were able to do in a 10-minute session. And what's interesting in this graph is we plot here the successful flips relative to the people who focused on the goal of the task, they were above the mean in doing so, or they didn't focus on the goal of the task. So in this deliberate practice group, they were told to focus on the goal of the task. But the people who really didn't follow that instruction did better than the people who did. And then conversely, in the play group, when we told people to not pay attention to the goal of the task, when they did that, they performed much worse than the people who kind of ignored the instructions and did focus on the goal of the task. So I was still trying to explain these findings, but the important point is here, if we were just interested in whether there was a relation between did you focus on the goal of the task and how did you perform, we would be collapsing these data points and these data points, and we would find no relation between performance on the task and whether people focused on the goal or not. It's only when we look at the interaction between this and the practice condition that we see this emerge. Okay, so let me speed things up a little bit here. The next section of the paper, we looked at research that's been done since the millennial, and basically what we found was that there's been a shift to describing the breadth of individual differences rather than trying to predict performance. When people have shown an interest in predicting performance, they've typically used a single dimension on which individuals differ rather than these big batteries of tests that were used by Fleishman and Ackerman. And it's interesting that there's been a lot of research that has been focused on talent identification and development that is very similar in many ways to the research that Ackerman and Fleishman were doing. So, people who are doing research on talent ID and development are obviously very interested in long-term prediction of performance and have done many studies designed to try to predict who is likely to reach the elite levels of their sport or their performance domain. Those approaches to that problem haven't been particularly successful, though, I have to admit. The other thing that really came out when we looked at what's happening since the millennial is a lot of research has been done in the neurosciences, and particularly around this idea of do differences in brain structure and function predict motor control and learning. And people are not just looking at the brain, but they're actually looking at the genetic level as well. And one of the findings that seems to come up is that variations in dopamine receptor genes and in genes that regulate the expression of brain-derived neurotropic factors appear to be implicated in individual differences in motor learning. We also have there's a paper that's going to be published in this special issue on individual differences that focused on neurodynamics and whether they predicted learning. So I just wanted to highlight that paper because the answer to that question was positive, that resting state neurodynamics do seem to predict individual differences on this virtual marksmanship task, particularly in terms of perceptual sensitivity to the task itself and changes or rates of changes in that perceptual sensitivity. So that's a very interesting finding if it replicates and it generalizes to other tasks. So what suggestions do we make for future? Some of these suggestions apply to any sort of research, not just research on individual differences. So we argue that people should study more complex tasks and study them longitudinally. We argue that people should use a combination of process and product measures, not just focus on outcomes as we tend to do in motor learning studies. We suggest that people might want to start looking at expert learning. And most of the research that we do in motor learning focuses on novices. And we know a lot about how novices learn tasks, but virtually nothing about how experts learn new tasks. We argue that people should increase their sample sizes. This is a problem that cuts across, again, all research in motor learning. And then we argue that people, from the statistical standpoint, should consider using mixed effects regression to study individual differences and use that to examine the between participant variability and model trajectories. So we have this figure in the paper where we provide this hypothetical experiment showing performance over time in a motor learning experiment. So here would be the individual participants, how they perform over time as a function of being in one group or another. So red would be one group, black would be the other group. And so we're just highlighting here the individual differences in performance over time. Now, what we typically do in a motor learning experiment is this. We'll analyze these data using something like an ANOVA. So we group data, we look at time 1, this might be a pretest, time 2 might be a retention test, and we focus on the group differences. So the individual differences then just become part of the error term in this approach. But in this panel here, we model the trajectories using mixed effects regression. And when you do that, you can still look at group differences, but because you can more sensitively partition the error variance, you can look at a number of other interesting facets here that are connected to individual differences. So you can look at differences in the intercepts where people start, in asymptotes, in the rates of change. So there's a lot more we can pull out using this particular statistical technique. And here we've gone a step further, and rather than simply just partitioning the error into different sources, we try to explain it with an individual difference variable. So the different colors indicate different levels of this variable. And in this case, we're looking at differences in the intercept, but we use the same approach to look at differences in the asymptotes or in the rates of learning. So just continuing on, we suggest that people need to examine the conceptualization of abilities and relation between skill and abilities. One question we might want to ask is, how stable are the abilities that we've identified? And have we missed any crucial abilities? Learning to learn might be one such ability. And in addition to abilities, we need to ask, how much does prior learning and transfer contribute to new learning? If we're going to focus on individual differences, we also need to re-examine our conceptualization of learning and transfer. I joke with my students that our understanding of transfer of learning hasn't progressed much since the classic 1967 Batman episode when the Joker learned to surf by using a transferometer, then challenged Batman to a contest, which he ultimately lost. Here's the transfer experiment, and here's the test. Then finally, we suggest that people should really consider doing research on aptitude treatment interaction. So again, what we're doing here is basically reprising Cronbach's call for more research on aptitude treatment interactions. We recommend using mixed effects regression, and we also recommend keeping it as simple as possible. For example, looking at a single stable dimension of individual difference to examine relative to a particular learning condition. And again, keeping it to something that's as stable as possible, rather than a latent variable like an ability that requires a huge battery of tests to determine. So that's basically the end. I know I covered a whole lot of territory in a short amount of time, and I wanted to leave some time for questions. So rather than say any more, I figured I would start there and I'll stop there and let you process and ask me any questions that you might have.
Thanks, David, for the great talk. That was really really interesting. I wanted to ask you at the beginning, you talked about that people typically compare abilities to initial performance as different ways of predicting performance. And it seemed like maybe it's like an unfair comparison because the abilities assumedly also affect your initial performance in the task. So I wasn't sure exactly how that worked.
Yeah, I mean, they would. Technically, the abilities should explain initial performance, mid performance, and late performance. So yeah, absolutely. The question is it worth the effort of trying to identify all of these abilities and use them as predictors, or would it be simpler to just look at how people perform initially and use that as the predictor? So you're right; those initial abilities would be confounded with how people perform initially on the task. But just from a very practical standpoint, the question is: do you invest all the time in trying to identify these abilities, or do you just say, "Okay, I know that I can explain a certain amount of variance late in performance just by looking at how they perform initially on the task"?
Okay, thanks.
Hi, thanks for the very interesting talk and just the primer on that research. It was very useful. So I have a somewhat related question actually to Jason. So you've highlighted towards the end that obviously we could look at, for example, the rate of learning, right, as one of the possible predictors of the outcome at the end. And I was wondering whether you have any research, or you know of any research that has done that in detail. So instead of just looking at the absolute level of performance when they start, which could be determined by expertise of all kinds of sorts and that type of variability, plus maybe genetics and so on. Have you looked at kind of the initial rate of learning and how it predicts the end performance?
Yeah, not personally, but this was a major question that people were asking earlier last century. And it relates to this idea is general intelligence equivalent to learning ability. So they were very interested in examining rates of learning, but they used gain scores to do so. So in gain scores, you basically look at initial performance and final performance, and you just subtract the initial from final to get that rate of performance. The problem with that is that because most tasks have a ceiling level, if you get somebody who performs well early in practice compared to somebody who performs poorly early in practice, the person who performs poorly has obviously a much wider scope for improving on the task, and this is why people at one stage thought there was no relation between intelligence and learning ability, because people with high intelligence tended to do better early in practice, and so they didn't show higher rates. But of course, that was probably because they just didn't have as much room to improve as people who did.
Yeah, it sounds
so.
Yeah.
So using, I'm not a specialist at mixed effects regression. Keith is the specialist in that area. But apparently using the mixed effects regression, you can overcome that problem of using gain scores. So when you model the trajectories, you can actually look at those rates and see to what extent they predict later learning. But as far as I'm aware, nobody has really done that, because nobody's been using mixed effects regression to do these sorts of analyses. All the past work has used gain scores, and the gain scores are problematic.
And do you think that the gain scores, if you were to focus only on the very early stages of learning, where you don't actually hit the ceiling as yet at that stage, they should be obviously less confounded in that sense and might be more pure? Would you disagree with that? Are they?
Yeah, maybe. I'm not sure. To be honest with you, I'm not sure. I think regardless of whether you looked at early, middle, or late practice, there's still going to be a problem using the gain scores as opposed to modeling the trajectories.
Okay, thanks.
I wanted to ask if you know of any practical examples of where people have used these sort of insights about individual differences to sort of guide people in motor tasks and how to perform them better. So I guess I could kind of take home message from this: if you want to teach someone better to learn better a particular skill, I don't know if you know if there are concrete examples of this where people have succeeded.
Yeah, so I say one of the best concrete examples would come from the educational psychology literature. Again, because there's not a whole lot of research in motor learning dedicated to this, it's, there are a handful of scattered examples I could find. But one of the findings that seems to be fairly robust in educational psychology concerns whether people who are considered high in ability, these would be people generally higher in intelligence, benefit more from a high structured practice environment or a low structured practice environment. And what that research consistently reports is that people who tend to be higher in ability, particularly in intelligence, tend to benefit more from practice environments that are less structured, whereas people who are lower in ability tend to benefit more from learning environments that are more structured. And the same seems to apply to locus of control. So people who have an internal locus of control, who think that their performance is really determined by them, tend to benefit more from less structured practice environments. And people who have more of an external locus of control tend to benefit more from more structured environments. So that would be one example. I think the contextual interference example is another really interesting one to think about relative to motor learning, because that essentially says that whether you're going to benefit from blocked or random practice depends on your cognitive style. So if you're already a reflective person, random practice is not going to help you that much. But if you are more of an impulsive person, random practice presumably forces you to be more reflective. It slows you down and encourages to think more about what you're doing. And so you do benefit from that random practice. So, those would be a couple of practical examples, but I really think we just clearly need to do a lot more research to be able to come up with practical examples that people might be able to go out and apply immediately. I think that the challenge point framework encourages us to do that, but it doesn't give us any specific guidelines. It just says that what we need to be cognizant of when we're designing practice is the complexity of the task and the learner themselves, particularly in terms of their information processing characteristics. So I think maybe the easiest way to think about practical applications with respect to challenge point is relative to younger versus older learners. So children clearly are going to be less adept at information processing than adults. And so you'd want to give them practice environments that are less challenging in terms of information processing than you would give to adults. And the same thing if we're looking at novices versus experts. Again, though, as theorists and practitioners, we've kind of got to do the work ourselves and figure out how to apply these things. Nobody's given us some really concrete guidelines to say, in this particular situation, this is exactly what you would do. And I think this is one of the reasons why you don't see too many motor learning researchers, at least right now, working in applied contexts, particularly in high performance sport and so on. I mean, people are aware of the need to have people who are aware of skill acquisition principles, but we don't get used very often because, unlike an exercise physiologist who can say, yeah, if you want your person to improve, you need to put them on this specific training program, it's much, much harder for us to do that. And I think it's harder because we haven't spent enough time looking at individual differences. And it's not until we really focus more on these individual differences that we can become more skilled at applying our craft in these applied settings.
Okay, thanks. Yeah, no, that was because I know we've been looking at some tasks where you let people explore themselves the timing, or you give them a fixed timing, and we see that in general, where you let people discover themselves the timing, they tend to learn more than the other group. But it's mixed. Some of the participants in the group don't show this behavior. It doesn't really help structure. So it's always been an interesting question why it works on some people and doesn't work on other people. That you gave me some good ideas to think about why maybe it works on some and not on the others.
Well, I mean, what you're doing, I'd love to hear more about that. But what you're doing is similar to that stick flipping experiment we did, where we kind of created this exploratory learning group versus a deliberate practice group, and yet there was all sorts of individual differences in terms of how people responded to those different practice conditions. And the most interesting things we found were, then the interactions between their practice conditions and some of the individual difference characteristics we measured. And had we just looked at the group performances, we wouldn't have seen very much at all, because a lot of the interesting stuff just got washed out when you look at the whole group versus the whole group.